Hey everyone, welcome to our latest edition of our live Q&A sessions with our astronomer Rachel. Hey Rachel, how's it going?
Hello, doing well, thanks.
Awesome. So this week we've got a really exciting theme for you. The theme this week is gravity, something that we're all feeling almost at all times, every existence that we have. All in equal ways, except for the various people that get to leave our planet and they get to experience gravity in other ways. But you're going to get into that in a little bit today, aren't you, Rachel?
I am, yeah, I gotta say, I experienced a little bit of weightlessness here floating outside in space.
Yeah, absolutely.
Microgravity, yep.
Cool, cool, cool. You always a little spoiler there, microgravity. So we've already got introduced some of the terminology, and for everyone that's watching on YouTube right now, so you'll be able to interact with us by typing into the chat. Maybe just try that right now. Say hello. Say where you're viewing from today. And then Rachel's going to give a short little presentation on gravity, and then we're going to get into your questions. And then we're going to open it up to any questions about the universe and or if it's relating to gravity or not. So Rachel, why don't you take it away?
Sure, I'd love to. So I'm just gonna share my screen right here. And while I'm waiting for it to load, I thought the best way to explain gravity would actually be to follow the scientific train of thought throughout history. So hopefully you should be able to see a nice slide that says gravity explained. So I'm gonna give it my best shot to explain gravity here. Now we begin our talk with Greek philosopher Aristotle, and he believed that all bodies move toward their natural place. Much like a rock sinks to the bottom of a cup of water, the Earth sinks into its place at the center of the universe. Now, of course, at this time, they believed that it was a geocentric or an Earth-centered universe. And this is actually the first time that we see the Latin word for gravitas, meaning weight or heaviness. And then next up, we have Galileo Galilei, a very famous Italian astronomer, physicist, and engineer. Now, the story goes that some 400 years ago, Galileo started dropping things off the Leaning Tower of Pisa, anything from metal spheres and gold to musket balls and wood. And he might have expected that heavier objects fall faster, like Aristotle did, but he actually discovered that all the objects he dropped hit the ground at the same time. So he made a big discovery. He found that gravity accelerates all objects at the same rate, no matter their mass or the material that they're made of. And what's really cool is that the Apollo 15 crew actually ran a similar experiment to Galileo's on the surface of the moon, which I did have a video for, but it looks like the IP address can't be found. But if you look up Apollo 15 hammer and feather drop, they actually drop a falcon feather and a hammer at the same time on the surface of the moon, and they find that Galileo was indeed correct. Now, about 100 years after Galileo's musings on gravity came Sir Isaac Newton, who had a light bulb moment supposedly under an apple tree. Now, imagine a cannon at the top of a very high mountain, just like we have here. Now, if it fired a cannonball and there weren't a force of gravity and no air resistance, then the cannonball would keep traveling along a straight line forever and ever, all the way off the screen. Now, but because there is a force of gravity, the cannonball will eventually be pulled back towards the Earth's surface and fall to the ground. Now, how closely it falls to the ground and how closely it falls to the ground towards the mountain depends on how fast we shoot the cannonball, or in other words, the horizontal component of its velocity. And the faster we fire the cannonball, the further away from the mountain it'll land. Newton then had this idea, well, suppose we fire the cannonball with just the right speed or just the right amount of horizontal velocity. Then you could, in theory, send it in orbit all the way around Earth. And gravity would make sure that it never escaped Earth completely, and the horizontal velocity will ensure that it doesn't hit the ground either. And what's even cooler is that if we launch the cannonball with an even higher velocity at a speed that's greater than a threshold that we call the escape velocity, then it could actually escape Earth's orbit altogether. And this led Newton to realize that the force that draws the cannonball towards the Earth and the force that keeps the moon in orbit around the Earth, or even the planets in orbit around the sun, are one and the same. Thus, he came up with the law of universal gravitation, which says that every object exerts a gravitational pull on every other object in the universe. And we can describe this pull in terms of their masses and their separation distance. Ooh, and it looks like my slide is still loading. Maybe I'm going to quickly try to stop sharing my screen and then share it again, and we'll see if that fixes the issue.
Always a good plan to restart when technology doesn't work so well.
Is it really a live stream if there aren't technical difficulties?
Yeah, absolutely. And if you don't get the video, I'll find the video of the hammer and feather drop on the moon afterwards.
That'd be great.
But yeah, everyone can see the comments rolling in, so keep those questions coming. I might as well jump in on one sort of.
Sure, yeah.
One question was, you were talking to us, how does it keep us on the ground? So, and you did sort of like explain a little bit, but maybe sort of like get specific on like how does gravity keep us grounded?
Sure. So I'll explain it actually from Newton's standpoint, and that was the idea that gravity is a force. Now, Einstein came later and actually described it as a pseudo-force, but you can imagine that because everything in the universe, all objects are exerting a force of gravity on all other objects, we are actually exerting a force of gravity on the Earth and the Earth onto us. So we're actually pulling each other towards each other. So I can actually write a formula using Newton's formulation of the universal law of gravitation between you and Michael and describe the force of gravity or the magnitude of that gravitational attraction between us. And I think that's really cool to be able to quantify the attraction between two people.
Yeah, I've always thought about that. If we were just floating in space and we weren't close to a sun or close to a planet, would a smaller object orbit a larger object? So if like, say you had like a baby and like a human, would the baby orbit the human?
Well, you're basically describing planets and their moons, with the baby being the moon, which is an interesting analogy to think about. And I think that I've gotten my slides back here. So let me try sharing my screen once more. And hopefully this is the only technical difficulty that we run into. Alrighty, so Michael, do you see the history of gravitational theory on a timeline?
It's almost loading, starting
Hopefully.
Yeah. Usually takes about 8 to 10 seconds. There we go. You're good to go.
Awesome. Okay, so we just finished with Newton describing gravity as this force, and it came up with this really nice mathematical formulation for that. But now, even though Newton's theory works really well in everyday situations, and even in not so everyday situations, like flying to the moon, Einstein actually had a problem with Newton's theory. And he was worried about this idea of spooky action at a distance. And you might have heard this before. And what this says is that according to Newton, gravity is a force that acts instantaneously over long distances. And what that means is that if the sun just happened to disappear tomorrow, the Earth would feel that lack of gravity immediately, hence the spookiness of action at a distance. But in Einstein's theory of relativity, nothing, not even a force like gravity, should be able to travel faster than light. So that means that Newton's theory can't exactly be right. So Einstein started trying to modify it. And that brings us naturally to the question, well, why do physicists prefer Einstein's theory of gravity over Newton's? And well, the result of many years of calculations and hard work on Einstein's part was not just a tweaking of Newton's theory, but actually the birth of a completely new one. And that was Einstein's famous general theory of relativity. He took inspiration from Galileo's idea that near-Earth gravity affects all objects in the same way. Einstein then thought that, well, if this is the case, then maybe gravity is not a feature of the actual objects themselves, but rather a feature of space-time itself. Now, general relativity says that massive objects like the Earth or Sun don't emit a gravitational pull or force, but instead, they actually bend or curve the very fabric of space-time itself. And this bending actually changes the way that objects move as they travel through a curved space-time. Now, if you take a look at this GIF, we see that we have an object falling in Newton's theory, which works in a flat space-time with a force pulling down on it. But we look at Einstein's theory, which works in a curved space-time, and the object's trajectory follows the curvature of space instead. Now, there's a very famous quote from physicist John Wheeler, which summarizes Einstein's paper on general relativity. And he says that space-time tells matter how to move, and matter tells space-time how to curve. Now, Einstein's theory also provided the answer to this very mysterious uh, behavior of Mercury's wayward path. Now, rather than orbit the sun in a closed loop like you see up here, Mercury actually travels around the sun in a shape that is close to, but not quite the same as an ellipse or an oval, so something more like down here. Now, Newton's theory was unable to explain this behavior, but Einstein's theory actually predicted it perfectly. Now, of course, general relativity has predicted many exotic and surprising phenomena like black holes and gravitational waves, phenomena that we've only recently begun to observe for the first time. Now, what are gravitational waves? So they're actually just these ripples in the fabric of spacetime caused by some of the most violent and energetic processes in the universe. Einstein's math showed us that massive accelerating objects, like neutron stars or black holes that are orbiting each other, would disrupt spacetime in such a way that waves of undulating spacetime would propagate out in all directions away from the source. And these cosmic ripples would travel at the speed of light, carrying with them information about their origins, as well as the nature of gravity itself. Now, while the processes that generate gravitational waves can be extremely violent and destructive, but by the time the waves reach Earth, they're actually thousands of billions of times smaller than when they originated. In fact, by the time gravitational waves from LIGO's first detection reached us back in 2015, the amount of space-time wobbling they generated was 1,000 times smaller than the nucleus of an atom. And we actually have a new space-based gravity wave detector that's set for launch in the next coming decade. It's called LISA, and it's shown here on the right. LISA stands for a Laser Interferometer Space Antenna, and it'll consist of 3 spacecraft placed in a triangle separated by millions of kilometers. And these 3 spacecraft will relay laser beams back and forth between them, and the signals will be combined to search for gravity wave signatures. And the reason we need a detector bigger than the size of Earth to catch these gravitational waves is because low frequency gravity waves actually have wavelengths that are much, much bigger than Earth itself. So a detector like LISA will be very sensitive to these low frequency band of the gravitational wave spectrum, which contains a lot of interesting astrophysical phenomena, things like binary stars within the Milky Way, binary supermassive black holes from other distant galaxies, and even lopsided mergers of a supermassive black hole and stellar-sized objects. Now, what I think is particularly interesting is that from the first direct detection of gravitational waves in 2015 by the LIGO and Virgo collaboration, we actually breached a new field of multi-messenger astronomy. And that's the idea that we can view or listen to our universe in different but complementary ways. For thousands of years, astronomy was limited to the naked eye for observations of the night sky. The invention of the telescope during the Renaissance opened up new avenues of inquiry. And by the end of the 20th century, the entire electromagnetic spectrum, all energies of light, became available for scientists to study stars and galaxies. But of course, we know that some of the universe's most mysterious objects don't actually give off any light, things like black holes. But they do have some sort of gravitational presence that we can detect instead. And what's even more rare is being able to detect the same event in both waves of light and gravity. And only one such major astrophysical event has actually been observed in both these messengers or sources of information, both messengers being light and gravity. And that was actually a neutron star collision in galaxy NGC 4993 back in August of 2017. And this image that I have on the right is this neutron star merger with data both in waves of light and also waves of gravity. And I think that's really interesting to be able to see the same thing in 2 different but complementary ways. Now, given the wealth of knowledge we've uncovered just from looking at the universe in waves of light, I'm very excited to see what we can uncover by listening to our universe with waves of gravity as well, especially with the heightened sensitivity of the space-based interferometer LISA and also collaborations like LIGO and Virgo. So I can't wait to see what else our universe has to offer. And with that, Michael, let's get started on our Q&A and talk about our universe.
Yeah, absolutely. So let's take this back just a second because we do have some interesting questions. And I think, when it comes to gravity, we kind of have to, layer on our understanding because we have sort of like the very basic concept like, oh, okay, gravity is keeping us down here on the ground. But then as we go out into the universe, we see that gravity gets a little bit more complicated. So one question that we did get in was in thinking of what is gravity made of? Now, you sort of described, gravity as being a force, and
Mhm.
certainly took us through the historical context of our understanding of it. So, can we think of gravity as being something that has something attached to it, or is gravity really just is it better to think of it as the effects that it has on the rest of the universe?
That's exactly right. So it's more of an effect. So that idea from John Wheeler saying that matter tells spacetime how to curve. So it's really, you can imagine like that analogy of having a trampoline being the fabric of our spacetime and putting
Yeah.
a really heavy bowling ball in the center. It'll start to warp or distort the trampoline surface, or in our analogy, the fabric of spacetime. And if you were to throw in a marble and give it some sort of initial horizontal velocity, it'll start to orbit actually around that center bowling ball. And that's exactly what's happening out there in our universe. So when Newton started describing gravity as a force, it was really this idea because it was a lot easier for us to wrap our heads around, because that was what we were used to. We were used to apples falling down on our heads because something's pulling it downwards. And so that was really the big revelation of Einstein, going from gravity as a force to gravity really as a pseudo force, which really arises from the consequence of distorting space-time and warping space-time itself.
Right.
Yeah.
That's really great, and that immediately sort of like gets me to wonder about what's going to be the next major shift in our understanding of gravity, because there's some big problems that gravity is showing us that our galaxies should be speeding up, but we have this dark matter that's like slowing them down, and that's because of our understanding of how gravity works now. But do we have it wrong? Or maybe is there going to be a shift in our understanding? What's your take on that?
That's why I really thought that bringing us through that historical perspective was really important, because, it's kind of funny to think that looking back at Aristotle and even Galileo Galilei, that giving our understanding now with Einstein's revelation, that we think that, oh, it's so obvious. Of course, it's acting on objects in different ways. But back in their day, they really thought that these ideas were correct, and that this, based on their understanding, that was the most amount of information that they had, so it must be true. And so for us to experience another paradigm shift in the future, I definitely think that will happen. And I do think that it'll happen with dark matter and dark energy, because dark matter and dark energy are really these umbrella terms for things we have zero idea about. We kind of know how they interact, we can see what they're doing, the effects that they have on things in outer space, but we have never made a direct detection on either of these things. So I'm thinking that the next big thing will be some sort of shift in understanding on our knowledge of dark matter and dark energy.
Awesome. Let's get through some of these questions. We might not have time for them all, but let's see. This is a really interesting question. We'll sort of start with keeping it here on Earth, and it has to do with water's capillary action in plants. Does gravity affect that? Is that something that you have any knowledge about?
Oh my goodness. No, I had never thought about that before, but I would imagine that there's some sort of movement that gravity has on that water, because I can't imagine that there would be like a muscle equivalent to move around water
Yeah.
in plants, as we do on our esophagus with peristalsis, moving food or boluses down our GI tract. So I'm going to have to say maybe on that one, given my limited biology knowledge.
Yeah. I
But I'm
guess
thinking, yeah.
I guess that would lead to the next thought, which would be, what would plant life look like on another world that had a different gravitational pull?
And even
You know?
with different star systems as well, I'm thinking different energies of light will affect the photosynthesis process on
Right.
different planets as well. So I would love to be the first person to be like Mark Watney in The Martian and go and colonize another planet and see if I can grow different vegetables there.
Right. When, of course, the next world that, I don't know if we're going to find plant life there, but on Titan, which is a world that we're going to be exploring in the next decade or two,
Mhm.
you know, if there was some sort of, I don't know if you would call it plant life, but something growing there, what would that look like? I find that really fascinating to think about.
it's bizarre to think of other life forms that are based on different molecules. Like I
Yeah.
think we mentioned this during our exoplanets theme week, but talking about the fact that we are carbon-based life forms, but there could be methane-based life forms that would thrive on places like Titan, which have methane lakes and rivers. And yeah, I don't know. It's kind of the mind boggles when I think of stuff like that.
Awesome. And another question that you would sort of like teased when you said microgravity, and that is something, of course, that when we see astronauts at the International Space Station, it seems like they're floating around. But of course, they're not in. There is not like they're not experiencing gravity. They are experiencing gravity. So maybe just like let us tell us what microgravity means and what are astronauts experiencing when they're on the International Space Station.
Sure. So the best way to think about this is going on a roller coaster, and you go over the highest bump, and then your stomach drops, and you kind of almost get that brief feeling when your butt lifts off the seat a little bit, that brief feeling of weightlessness, and that's actually what the astronauts on the ISS are experiencing. Because in reality, the ISS orbiting the Earth is actually the ISS continuously falling around the Earth, and they have just enough horizontal velocity to keep them in that stable orbit where they're constantly falling around and orbiting the Earth. So it's that kind of same idea, that that feeling of weightlessness, that feeling of falling, that the astronauts experience because they are in this low Earth orbit around 400 kilometers up in the sky around Earth.
Awesome. Let's get through some of these questions. I think this question is talking about Newton's theory of horizontal velocity, and I think what the question is, how could he prove it, or how could we prove horizontal velocity when it comes to gravity?
Ooh. So I believe from knowing about Newton's upbringing and his kind of a philosophy of tackling problems, he, especially in his Principia, which was his greatest paper that he published, he often tackled problems from a geometric perspective.
Right.
So my idea would probably be that he was calculating these horizontal velocities and trying to figure out, well, to maintain a circular orbit, you need some sort of minimum horizontal velocity. Like in that example, we were talking about a cannon shooting a cannonball at some sort of speed, that you do have this threshold speed, that you have this perfect balance between Earth's gravitational pull inwards towards its center, and also that horizontal velocity wanting to continue in this straight line. So that brings us back to the idea of the ISS orbiting, constantly falling around the Earth, because you're constantly experiencing this tug, but you're also constantly adding that horizontal velocity. So it's really this balance to be able to figure out things like an escape velocity, which is essentially the horizontal velocity that you need to maintain or exit Earth's gravitational pull.
Right. Interesting. Let's keep going with some of these questions. I like how this is worded. When does gravity end in space? Now, you could also say, where does gravity end in space? But I like how that's worded. When does gravity end in space?
I like that too, because I like to think that that's a very similar question that Newton asked himself,
Yeah.
with this idea of spooky action at a distance, like Newton saying that everything exerts a force on everything else, even if it's 93 billion light years across the universe, is kind of an absurd idea. And now with this formulation of Einstein's theory of relativity saying that gravity is more of a local property. It's a local property of the fabric of space-time. So as long as you're experiencing any sort of curvature, that's when you're going to be experiencing gravity. And the magnitude or the strength of the force of gravity is proportional to exactly how much curvature you have. So it really depends on how much curvature you're experiencing in the fabric of space-time, which, because there's objects all around, is pretty much all the time.
Now, of course, if we were to think about sort of, where, is there a place in the universe that could possibly be? And I'm starting to think, well, maybe at the edges of the universe where where the universe is expanding. So there's that dark energy that is forcing the entire universe to expand, which is kind of overriding any gravitational force there might be from, say, like that dark matter. So, and that energy is winning out, right?
Exactly. So I like to imagine that perhaps when does gravity end? That question would be in ultimately our universe will keep keep its accelerated expansion. And so eventually, in theory, our nighttime sky will no longer see anything else in our nighttime sky because things will have expanded so far apart that they're too far for light to travel between things like galaxies or stars. So in theory, if we do end in what we call this heat death of our universe, which sounds very ominous, but it really just says that things are so far apart, that perhaps maybe that's when gravity will end, because all these massive bodies are so far apart that they don't exert this gravitational influence. They don't have this curvature experiencing locally around yourself.
Really interesting. Really, some really interesting questions. Of course, our fellow staff member Pablo chimed in, which I think was an answer to the plant question, which is the hydrogen bonds, which of course are causing, which I believe is that sort of the answer to the water question probably. So does gravity have more of an effect than the bonds of hydrogen atoms? I think is probably what that answer is.
Oh, interesting. Yeah, because hydrogen bonds are very strong. So I would assume that in terms of on that scale for plants, hydrogen bonds will win out over the force of gravity.
Um, cool. Here is another question. This one might be a bit complicated. Let's go back to gravitational waves, because you did talk about them for a while. And talking about space-time fabric like it's a 2D plane. Should we not conceptualize space-time as a 3D fluid in which we're sinking into or being thrown through?
That's a great question. And this is where the analogy of the trampoline fails, because it's a 2D analogy for something that's really, in reality, it's four-dimensional, right? We have three spatial dimensions where we measure X, Y, and Z coordinates. And we also have the time or temporal dimension that we also have as a coordinate axis. So it's really difficult for humans to imagine something that's four-dimensional, because we can experience the passage of time. We mark it by event 1 and event 2 and seeing how much time passes between those. But it's very hard for us to find a perfect four-dimensional analogy for the fabric of space-time. So for now, we make do with projecting that onto a 2D surface like a trampoline.
Right. And so I guess, as our understanding of something like gravity, starts to expand, we also need to change our models for that as well, which does tend to get very complicated when we try to explain it. And I suppose if we did go back to, that question of how did Newton, prove these things? Well, he had to create new models for our understanding, right? So if we were to change our understanding of gravity, we would also have to change our models. What would we need to do that? Do we need artificial intelligence? Do we need something sort of like to help us visualize these things? I'm not sure I know what the answer to that is.
I'm not sure I do either, but I don't know if I'll ever be able to imagine a four-dimensional object. So for now, I think we'll have to make do with some slightly imperfect analogies that do their best at trying to explain a complex topic.
Awesome. Well, we've pretty much come to the end of our live stream here. Of course, if you have any more questions, I love the chat that's been going on. Lots of people talking back and forth. I love it. Hopefully, everyone that's here today is subscribed to us, because we're going to be live every week at 2 o'clock. I'm glad that you've all come back here. So check us out, 2 o'clock every Thursday. We have some announcements coming up, because we've got some special events that we are going to be announcing. We've got a next Cosmic Night coming up. I'm not going to let you know which one it is, but I might give you a hint. It's about black holes. And that is going to be being released. So stay tuned. Check our website on the information for that. We've got some special speakers that are going to be coming up about black holes next week for our live chat. What is our theme for next week, Rachel?
Living in space,
Yeah.
just like I am right now.
So we're going to be delving into all about the nuances of living in space. So once again, come back to our live Q&A for questions on that. And of course, if you would like to donate to us, because we are a nonprofit and we're doing all these programs for free on the internet here, we really appreciate your support. You can go to our website, spacecenter.ca, go to the Donate Now button, and hopefully we'll be able to see each other in person soon. Hopefully see you, Rachel, in person soon. But for now, my name is Michael. Take care.